So this is a really interesting take on a language that's supposed to be secure. I spent about a year, a little bit over a year, actually about a year and a half now, researching the internals of Erlang to try to figure out how it could be attacked, which is really fun because Erlang is supposed to be a secure implementation of a distributed parallel processing language. It has a lot of benefits internally just from being able to distribute code over a large space so you can have massive amounts of nodes performing processing all at once. It's also an interpreted language. It actually runs inside of a virtual machine called Beam. But the language definition itself negates the ability to perform significant types of attacks that you would normally see in regular languages. So the cool part, if I can get this thing to work, which it's not, somebody want to flip the slides for me? It's just wildly going. Okay, cool. Well, we'll get back to that in a second. But I just wanted to jump into the core of what Erlang is all about. So as Emmanuel was talking about Erlang briefly, some of you may or may not know this, but the beauty of Erlang is that everything runs Erlang and nobody has a clue that it's such an important language. How many people here have actually heard of it, except for the last talk? Okay, so a few people, that's great. The elegant thing about Erlang is that it's been used for decades without very much of a change to the core language itself. It really hasn't needed it. Every major telco infrastructure that you see today runs Erlang without us even having to think twice about the infrastructure itself. So it's a very elegant, long-used language, and it eradicates a lot of the vulnerabilities that you normally see in programming. So in Erlang itself, it's kind of a secret garden. The security model of Erlang is quite simplistic in that once you have the ability to execute code, you can literally do whatever you want. The security model is you can't execute code without the ability to connect to the node network. So unless you have these cryptographic keys or secret cookies or whatever to connect to a series of nodes, you can't do anything in the network. That seems very simplistic. Well, it is, right? Once you get a node access, you basically not only have code execution inside the virtual machine itself, but you also have the ability to run code on the host operating system in most cases. There are certain environments that limit that, but most often you'll see code execution pretty much wildly available once you are inside of the virtual machine itself. Without significant patching, there's really no way to specifically say, hey, you can disable the ability to execute code outside the virtual machine. So if you're using a default install, which most people are of the language itself, you will be able to get code execution everywhere if you can get code execution within Beam. So the risks of Erlang make it a really elegant language resilient from attacks. So all the vulnerabilities that you would normally see in programming languages have been eradicated by Erlang's programming model. Once it's interpreted, your program, all variables are write once, right? So you can never write to the same variable twice. The real truth behind that is a little bit more complex. If you interpret the actual code that runs the Beam virtual machine, it doesn't quite work that way. It presumes that things work that way, but there are certain instances where variables are actually written twice. But we're not really going to get into that. The point that I'm making here is that the literally only valid way of attacking Erlang remotely is to do one of two things. Number one, load code into Erlang, so you have the connection keys. Or number two, you have access to a vulnerable function inside of the virtual machine itself, which there are several. I did a talk at LambdaConf last year that exposed some critical vulnerabilities inside the Erlang virtual machine that I also got Ericsson to patch. Those could be triggered in certain circumstances to get remote code execution, but it was really difficult to do it. And only like APT style attackers like myself would be capable of doing that You're not going to see random people doing that kind of thing. So in the realistic Erlang environment, all nodes being essentially under the same security domain, the only viable way of really attacking Erlang is by connecting to Erlang with a valid security token. It's really the only way to do it. So in the Erlang security model, once you have that token, that cryptographic capability, there's nothing else to do. So there's an interesting point that I want to make on this slide about monotonic timers. So monotonic timers are a source of entropy for building the security tokens for accessing Erlang. That's going to come up in a minute when I talk about the way to exploit Erlang, because that's a feature of the virtual machine or virtual beam operating system that's entirely guessable. Because monotonic timers are only one way, right? They're not arbitrary. They tick in one direction. Well, if you know that things tick in one direction, and you know about when that monotonic timer is going to execute, you pretty much can guess when that particular timer is going to execute within a window that's valuable to you. And you probably know what the value is, right? So let's get straight into it. I was going to do a demo, but we're having problems with my iPad, apparently, on this trip where I can't ever connect the iPad to the projector. So we're not going to do the demos. But it doesn't really matter, because you don't really need to see the demos. It's really just a pretty script anyway. The results is that no matter what the security cookie is or security key is to log on to a remote Erlang instance, you can guess it in about 10 minutes max. That's it. Doesn't matter what the particular service is. All you have to do is figure out essentially the timers that are used to generate the cookie that was then used to construct the Erlang node. So there are a couple of really important tricks that are necessary in doing this. And one of them is the use of atoms. So anybody here familiar with Erlang atoms at all? No? Okay, so there's a really cool feature of Erlang where basically every string is turned into an object called an atom. Now an atom is really just a fancy list. So like any language, you would have an array of bytes, right? Well, an atom is essentially a string that a list has been turned into. Well, atoms themselves are like every other variable in Erlang. They're write once. So they aren't rewritable, and they're permanent. So they basically sit in memory forever. So what's fascinating about the structure of an Erlang virtual machine is that over time, every time an atom is created, it will sit resident in memory until that Erlang instance dies. So when you think about all the things that are resident in memory in Erlang, there are a lot of critical tokens that will eventually become atoms at some point in their life over the span of that Erlang instance. And all of those things become atoms in ways that you can use them. One of them being the node name. So when you launch a host machine of any type, whether it's a Linux host machine or an Erlang host machine or whatever, everybody has a host name, right? In Erlang, you have a host name as well. That's also called the node name. In Erlang, node names, the string, Don, B, whatever, is converted into an atom, right? So a write once, read only string. The cool part about using that is the timing model of putting together an atom. So think about it this way. You've got a string, right? Essentially a list of characters, and you want to convert it into an atom. You already have an existing table of atoms that's write once. So you're going to check to see if that atom already exists. If it does, you're not going to write it again. You're just going to drop and say, okay, that's already been written. I don't need to do anything further. So if you're submitting these names remotely over a network connection, you can determine which atoms exist in a system already. So basically, when you connect to an Erlang node, it presents its node name, and you send your node name. Hi, my node name is DonB1, right? It takes that message, converts your node name into an atom, and then submits that to the atom list. If that atom already exists, it drops it on the floor. If it doesn't exist, it essentially creates memory space allocates the memory space within the atom list, copies the data over as an atom, changes the metadata, and then returns. In other words, there's a lot of crap that has to be done to convert a name or a list into an atom. So the result is a very significant timing attack. But why is that important? Because the cookie or the security key is converted into an atom, right? So basically what you can do is connect to an Erlang system, submit your node name, but submit a node name that looks like a cookie, and then do that over and over and over and over and over and over until you basically exhaust the atom space finding this particular key. Now, that would seem impractical, right? That doesn't really make a lot of sense, except that cookie generation is 100% guessable on the majority of cloud environments. And the reason why is because there are two keys that go into the creation of a cookie. Number one, the monotonic timer that I talked about a few minutes ago. And number two, an arbitrary integer that's basically created from a minimum of a couple of bits, right? Not really a maximum. I think there's a maximum of like maybe, 7 bits or 15 or something like that. It's a ridiculously small amount of entropy. But regardless, most of the numbers are predictable. So you can essentially create a window of about 1 megabyte. Like there's about 1 megabyte of options, of possibilities that the cookie will be generated by, right? And the cookie is then converted to a long string of characters, which is essentially very similar to base 64. It's like base 144 or something. I can't remember the actual number. Doesn't matter. It's just alphabetic characters. So it's essentially, for all intents and purposes, a string. So you have a minimum amount of characters that you have to guess. So now you've basically taken, okay, I can submit cookies over and over and over and over and over and over to I can only submit cookies within this 1 megabyte window. Well, how long does it take to issue 1 megabyte questions to a remote server these days? Not very long. And the entire point of Erlang is creating a distributed mesh of systems, right? So usually in an Erlang environment, you don't have just one server. You have 3, 5, 20, 100, 1,000 servers, all with the same key that are all distributed across the network. Well, if you can access one of those nodes, it's very likely that you can access multiple of those nodes. So now you can send your messages across a wide array of systems and basically recover the key in seconds. So that's pretty awesome. The other thing about this attack is it's entirely stealth. So submitting your node name during a connection to an Erlang instance requires absolutely no intervention by the administrator whatsoever. So there's no message, there's no log message that comes up, even if you have debugging turned on. There's no log message that actually states, hey, there's somebody that's pounding your server with requests, and those requests are turning into atoms. Nothing like that will ever occur. So basically, you can just completely repeat this attack over and over and over across as many systems as you want within that 1 megabyte window. And not only will you be able to guess the key, but you'll do it without notifying anybody, as long as they're not looking at TCP dump obsessively. But even if they are, if you're looking at a large distributed system, it's normal for systems to reconnect and connect and distribute keys and do all this stuff over and over and over, because that's the part of Erlang. It's a self-healing network. So if there's a problem with the network, a lot of this traffic is actually quite normal. So what's not normal is, host names that look like cookies, which are just long alphabetical strings of nonsense, right? Usually node names have some kind of normal format. So that's really the only give. Everything else is entirely stealth. So putting it together, say you have a cloud environment in DigitalOcean, AWS, whatever. Those environments are fingerprintable. So you can guess what the monotonic timer is going to look like when that Erlang instance boots for the first time. You can then guess what the pseudo-random number generator is going to guess within a certain number of bits for that particular type of cloud instance. Because again, they have very limited amount of entropy once they boot. These guys aren't using, true random number generators to seed all the virtual machines. That's impossible. So they basically have a minimum amount of data, especially in the Erlang node, that will allow them to generate a useful security token. And then once you have that window, you basically just create the amount of characters that are going to work for you within that window of searchable cookie names, and then you just start submitting your keys. You submit them over and over and over as node names, and then check the delta to identify which tokens are likely already atoms inside the virtual machine. Once you find that and you see the delta is different, it's much, much shorter because it didn't have to generate the memory to store that atom. You can drop the connection and then reconnect trying that cookie. If it doesn't work, try the attack again, keep iterating until you find another one. So that's literally it. That's all you have to do. So I basically spent a year and a half hacking all the internals of the virtual machine, analyzing the memory management system, analyzing the networking stack, analyzing the way it interprets integers, looking for integer overflow problems, all these complex things. And yeah, I found a couple of bugs. There were a couple of great bugs that were to be found. Fred Hebert on the Heroku team, brilliant, brilliant researcher and engineer. He actually found a bug that I missed in binary to term, which was something that can be triggered remotely and is often used in Erlang web processing, where you end up taking this opaque binary object and you translate it into a term. And terms in Erlang are, again, an array of different types of objects like lists, like binary packets, like atoms and things of that nature. And he figured out that you could basically take like a 2 megabyte packet and it would explode into about 4 gigabytes of a valid binary object because the binary to term processing allowed for zlib compression in the actual compressed binary object data. So there were a lot of bugs to be found, but none of them were really truly exploitable as in a one-shot remote compromise. We weren't ever able to find that. I was never able to find something that clean. This is the most clean thing that you could do, and it's also the easiest thing that you could possibly do. So it's basically like do all this insane research, and then at the end of the day, I just realized, oh wait, this is a really simple hack because of the design of the Erlang system. So basically, every single instance of Erlang today is vulnerable. I notified Ericsson of this a year ago, and they admitted that the remote atom thing was a problem. But based on the architecture of Erlang's virtual machine, it's so difficult to change the way that they're interpreting names remotely from atoms into something else that it hasn't been fixed. They've basically just said like, well, we're probably not going to fix this. So this bug is going to be abusable pretty much forever until they decide that this is an attack that shouldn't be abusable. The issue is really that there are technologies like RabbitMQ that use Erlang under the hood that recommend this style of generation of cookies. So I should be very clear, when you deploy Erlang, you can use your own cookie, you can specify your own long cookie string, or you can automatically generate one through Erlang system itself. If you let Erlang generate one itself, it'll use the monotonic timer model that I just talked about, and that will be the way that it generates the key that's then guessable. But most systems recommend that you do it that way so that you don't have to mess around with generating your own keys, and they also don't want you to generate weak keys. Now, most likely, people are going to use this model and think it's okay. I mean, RabbitMQ, even in their documentation, recommends this model for generating a cookie because they're presuming that the amount of bit space that's available in these keys is going to make it impossible for somebody to ever guess it, right? Like it's over 128 bits. Like nobody's ever going to just land on this remotely. But within that window, based on these vulnerabilities, it's absolutely hittable and it's even searchable remotely in the Erlang's virtual machine. So everybody recommends this standard model of generating code or generating keys. And nobody's really researched as to whether or not it's viable beyond just saying, is the bit space large enough? Yes? Okay, well that's fine, good enough. So Robert Graham, a friend of mine, you probably know him as ErrataSec. He did me a favor last year and scanned the entire internet using mass scan to identify how much Erlang was accessible from the internet. And we found just under like 250,000 machines. So it's not a large amount by any means, but it's still enough accessible worldwide that this is a pretty significant problem. Because these are telco systems, right? As Emmanuel mentioned in the previous talk, Erlang is used to run telco infrastructure worldwide. That's the reason why Ericsson developed it, was to run telcos. As I mentioned at the beginning of the talk, LT infrastructure uses Erlang, 3G, old GSM. All of these great technologies require Erlang in most cases to run the MSCs, HLRs, all of that great stuff that we use in order to ensure that systems can actually communicate. So a lot of these instances we found were, you know, I would say about 10% of them were people just messing around with Erlang or some kind of development instance or something of that nature. But somewhere around 30–40% were systems that I would personally consider critical. So it's still useful for people to understand that Erlang is not a technology that you should ever put on the public-facing internet because of issues like this. So there are a couple of cool assists with this technology that help make it really a great exploit. One thing that I didn't mention about the atom attack is that there is a maximum limit of the number of atoms that can exist in a system. Well, I think I mentioned that, but the thing that I failed to mention is that once you reach that limit, which is about 1 megabyte worth of atoms, and I don't mean 1 megabyte in size, I mean 1 megabyte total number of atoms that can exist, the virtual machine will actually dump core and exit. So it'll just say like, I give up, I'm done. And this is something that's existed in Erlang its entire life, right? They've never fixed this. You can actually increase the Erlang number of atoms that are available in the system, but most people don't because you don't necessarily need to. Most atoms aren't just generated over time, so this usually never becomes a problem, right? But it's great for exploitation because a lot of instances will have administrative nodes or logger nodes or things of that nature. And if you want to get really tactical about it, you can basically pick all those off by using this atom bug to remotely connect over and over and over with node names, have them converted to atoms using arbitrary host names, fill up the atom table, and then kill all these administrative processes. So every time you see a new administrative process spawn, there's actually, for those that don't know, there's the equivalent of a port mapping daemon called EPMD. And this service basically tells you where all the Erlang instances are and what their names are. So you can query that over and over, and every single time you see a new name that pops up that says logging or admin or something of that nature, you just point your code at it and kill it. Crash it, watch EPMD, see when the next one comes up. Okay, new one's up, found the port, found the host address, go point your code at that again, crash it, done. Over and over and over and over. So you can basically lock administrators out of their entire Erlang environment if you do this correctly, which is pretty great. The other issue is that when it dumps core, all of your exploit details are going to be stored within that core file. So it's not like Unix core. When you dump process in Unix, you get basically a binary core image of what that process looked like in memory. Not quite the same in Erlang. In Erlang, they have a big chunk of text that shows you all of the virtual machines registers and all this other stuff. And then afterwards, they have a binary payload for the entire region of memory. And all of that stuff is then auditable by somebody that knows how to reverse engineer it. And those guys are still around. So somebody will be able to actually interpret this and figure out what your attack is. So there's a clever way around that for people that are running in environments where antivirus technology is available. You can basically just put an EICAR test string as one of the node names when you connect. And then when it dumps core, it'll dump the EICAR test string. And if an antivirus signature or application is on the server, it'll basically see that as a virus and delete it for you. So then you won't have to worry about somebody interpreting your core file, which is pretty cute. That usually only works in 2 environments, and that's like corporate Red Hat, where people are running like ClamAV, and then when people are running Erlang on like Windows infrastructure, which does happen more than you'd think. But that's more like academic environments and some scientific research environments. It's not necessarily like telco infrastructure. So that's still kind of a clever little hack. But overall, Erlang is probably one of the best languages and most resilient languages that I've found for developing applications. In fact, I'm using it more and more these days to develop tools at Loudmouth Security because I actually really like it a lot, which is one of the reasons why I'm hacking the shit out of it. We're also using it in IoT infrastructure. We have our own IoT platform that we've developed from the ground up, and we're using our custom Erlang virtual machine in order to run nodes in our IoT environments. So instead of running some large application processor, a 64-bit processor, or even a large Cortex A5, it costs $12 a pop. I can run Erlang on my own 32-bit virtual machine inside a Cortex M3 for $1, right? So we basically just take our own virtual machine, put it on our IoT infrastructure, and then load and run it there. I mean, it required me to run or to code my own Beam, but who cares? It's a lot safer to run that Erlang code on IoT infrastructure than it is to just get somebody else to run embedded C. I mean, that's a shit show, right? So much better to do. Also, Erlang is super fast to deploy, which is one of the reasons why I think that nobody's ever stumbled across these bugs before. Because it's really easy, and if you look at the bit space, you have this really powerful language that's interpreted but also fairly secure. You're just going to assume that it's resilient. So that's about it. It's a great attack, but it's going to be very, very difficult for Ericsson to combat this in any way. Their recommendation is basically just going to be, you know what? Don't ever put this on the public network ever. In fact, when I was interacting with them via email, their response was essentially, well, I mean, there's value to this, yes, but nobody should really be putting these on public-facing networks. And that was kind of the end of it. And I gave them a year to think about it before releasing the information. But there you go. In my world, and I'm sure in everybody else's here in the room, we're not just worried about people that are knocking on the public-facing door, but also somebody that's migrated laterally in an internal network. So for the purposes of connecting to a system like an Erlang network, where they can abuse telco infrastructure to do malicious things. Like, that's still a significant concern. So if somebody can abuse these attacks internally to gain access to an Erlang telco network, it's still really important to guard against that. But apparently that's, their recommendation is probably going to be, well, subset that even further, put in some kind of secure internal network. Like, well, it's not realistic, right? So that's about it. Any questions?
Any questions? Mike is on its way. No questions?
All right.
Okay, well,
Thanks, everybody.
thanks, Don.
All right.